of this kind, modulo this, then you will never be homotopy. So you want some way to, so this is kind of how we circumvent it. By putting in these things turned out to be the right thing based on these examples. But yeah, if you drop this condition, probably there might be some claim like this, but then you have to impose something. What exactly you want to impose in an efficient manner, I don't know. Yeah, you need this. Yeah, in case there are, okay, in case, no, in this I can take it. Yeah. Okay, so this is, let's say, one particular connection to Morse code function and these. Let me now go on to a few other. Yes, in particular, when you are really trying to do something like this, well, what happens? You have two critical sets, and one of them is the global maximum, the other one is the global minimum. So when you look at their normal bundle, and what is the normal bundle of this at some point is going to be the boundary of that is going to look like the boundary of the normal bundle of this. So you have a common space which is fibered over two spheres of different dimensions. Fibers are also spheres of appropriate dimensions. And we have to use some homology, some spectral sequence or non-exact sequence. Somehow show first that n is going to be interconnected, and then you show that the homology of n is that of the set, and then you can some version of space here to show that n is actually going to be homomorphic to a set. So it uses the fact that if you have a synthetic manifold which has the homology of the set, and it is it's not possible. But yeah, basic things to establish the homology of n is that of the set. N is connected are fairly standard once you see what it says. Okay, so keep this sort of mind separately. Now we're going to see more examples again of Morse code. This will be slightly different in shape. Are there any questions regarding this statement? Well, there are some manifolds, so just homomorphic is good enough. Yeah, so this is the disjoint union of connected submanifolds, and claiming this, if you assume this is not S0, it's S0 is 2 points. Otherwise, it has two components, each component is homomorphic to a topological sphere of differing dimensions. Because at the end, I cannot even claim something about the structure of them, even if they were diffeomorphic to the standard thing, because this is living inside N. So standard means that this should have something, restriction is the standard. Even then it will not be true because the classical Gibbs theorem is false. But you can ask, okay, what happens if I tweak this a little bit? If I put CPK and CPL, do I expect them to be some CP something like that? Because essentially, I think at the heart of this, the driving force happens to be that the homology of this is simple. In the sense, those who have seen homology rings, the homology ring of this is generated by one element for a set. Same for CPL, same for RPL, with appropriate proportion. That simplicity is somehow helping the calculator. They have to establish that something with that homology ring looks like the candidate of. But yeah, any other? No, so yeah, that's what I mentioned here. The Morse code lemma is that if P is in N, then there is a neighborhood of P in N and local coordinates, so that F in that neighborhood looks like F of dash is F of whatever the value of f is taking on f, on n it's a constant. And then minus a bunch of negatives with negative sign squared, 1 through lambda, so lambda is negative. And then the complement is positive y is. So yeah, so that is what I meant by the Morse-Watt lemma. I didn't state it on that document, but two sort of quote unquote a parameterized version of the Morse-Watt, but the two sort of doing the so yeah, in this paper there's sort of doing reasonably clean. Any other questions? Oh, okay. So yeah, so the examples that I broadly want to consider are so, I mean, so far so good. Hopefully people are okay with manifolds, sub-manifolds, but I'm now going to be in the category of smooth manifolds. So think of it as this, everything is in Rn and we want to do something like that. So you can imagine Sn and some equator in Sn as you something. But now I'm going to sort of manifold here with which interchangeably are denoted by G or a bracket. So you have seen this very briefly yesterday. So what is the Riemannian metric? So essentially, it's not the same as a classical metric, which gives you distance between 2 points. But what it is a more refined data. So it says that at every tangent space, you're given an inner product, positive data in binomial form. And as your point varies, this inner product of EPM varies in an appropriate fashion. That is what a Riemannian metric is. Using that, you can define lengths of curves on your space. Right? You have a curve from P to Q, say gamma T. You can differentiate gamma T at every point, you get gamma prime. That's a tangent vector at some appropriate tangent space. You can evaluate its length using the metric. And then you can integrate that from 0 to 1. That's how you define lengths of curves on M using this term. And then you declare the distance between 2 points to be the infimum of all piecewise smooth curves from P. That's how wants to check that that's the distance and all of that. And so the topology that you get from that V should of course agree with the topology that you started off with. But that's how you get the classical distance on M by making such a choice. So yesterday you had seen that on Rn, all tangent spaces at every points are canonically the tangent space at the orange because you can translate. But you could put a different positive definite matrix at different points that will scale the vector appropriately. And that was happening in the point setting. The vector which was unit length at some point is not going to be unit length, even if it looks unit length. Anyway, so this allows, so the point of this thing is, this allows us to construct a distance on M. And I'm going to call it E. Okay? And at some point, I'm going to assume that this M, the ambient manifold, is complete. So, for those of you who know this, it's fine. There's, the classical result of Hopf, who says the completeness in the topological sense and completeness in the sense of geometry are one and the same. So, you know what it is fine. Otherwise, complete means complete in the there's no point getting into this. So, yes, and then we consider this part, d squared n. What is this? Given a point P, which has the distance this is the distance of the point P from the subset N. So far, I don't need any clear subset. Don't include any subset. Usually, I go subset and you compute the distance of P to N and then make it square. What is this? Remember, this simply means you look at all DPQ and look at the equivalent of DPQ as Q and the square of it. Right? Okay, so I think sometimes this is also denoted by square n is f. Right? So this is the distance with respect to n. And I'm going to hopefully exhibit a few examples where after the three examples will be somewhat convinced, it's not totally convinced, that this is a function which people outside of geometry study for obvious reasons. Why the square? Well, the square is there for a reason, then you want this to be different.